Good afternoon, this is Schweitzer, and we're going to run through a couple of just a little more application type problems that you should be trying to see how you can figure these out. Some of them got a couple little glitches, but it's one of those things where once you see the path and it's just some plug and chug problem. So, um, 5 kilogram block is dropped for 1.5 seconds. String is attached to a massless, frictionless spool. So, some of those details that we aren't too concerned about yet, but this essentially is dropping via gravity. So gravity is pulling this thing down. And what's the total distance it unwound? So this is just a linear situation where we have xt equals xi plus vit plus 1/2 at squared. Start from rest, so 0, 0, and I have 1/2 and then negative 9.8, and then my time is 1.5 seconds squared, and you're going to get a distance in meters, which is, I believe, 11 meters. Okay, so now keep in mind the gravity, this is going faster and faster and faster and faster, and it would really start picking up speed, obviously, due to gravity. So at this point, we have 11 meters. 11 meters. How many revolutions do we undergo? What's the final tangential speed of this thing? All right, so if I were to go 11 divided by, let's say look at this one. If I were to go 11 divided by 1.5, this would actually be our average acceleration, our average velocity, and we don't really want that. So let's take a moment and let's solve up for my final velocity. So it's going to be Vf equals Vi plus At. Start at 0 plus negative 9.8 to 1.5 seconds. And this is going to give me my final velocity at the end. It's going to be more than, it starts at 0. So 9.8 times 1.5. So I have an ending velocity tangential there of 14.7. Of course, the negative just means that it's going down. So the final tangential speed is not that. Okay, it would be the 14.7 meters per second. Okay. So, all right, so let's do a couple things here. How many revolutions did we go through? All right, so let's think about that for a moment. Let's go back to our basic formula. All right, so then we have circumference is equal to the angle traveled times the radius. So we've traveled 11 meters around the circle, and the angle is 0.1 meters. It's not a very big circle, so the amount of angle I've gone through is a bunch of circles, a bunch of revolutions. Divide it out, and 110 equals my amount of angle I've traveled. And keep in mind, 6.2 angles is, or radians, is 1 revolution-ish, approximately. So let's convert the 110, and because they want to know revolutions. Get rid of the radians and go to revolutions. 1 revolution is 2 pi, of course, radians. That's something we got to know. So 110 divided by 2 pi, 110 divided by 2 divided by pi is 17 and a half revolutions. Okay, so 17.5 revolutions are what we're looking at here. So 17.5 revolutions. Okay. Now, what's my final angular velocity? Now, you should keep in mind that my angular velocity is how much angle I am rotating by, and that's actually changing as we go by. So I'm looking to see, it gets more, the rate at which I'm changing. I have an angular acceleration caused by the gravity. So how would I figure this out? Well, I know my final angular tangential velocity, and that is equal to the change in angle times distance which is r, that's this formula right here, divided by time. So that is something that we've used. So in this case, change in distance, change in time, that's at the very end I have that value. That value is 14.7. So this right here is my angular velocity. So this is 14.7 times equals the angular velocity times my radius, which is 0.1. So I have an angular velocity of 147 radians per second. Looks like 147. Okay, this thing's spinning pretty quick at the end. Beginning, not so much. What's my acceleration of the block? The acceleration of the block is gravity. So I guess you could say, I should probably preface this as being, what's the acceleration? Well, acceleration is negative 9.8 meters per second of the block. Okay, yeah, squared. What's the angular acceleration of this spool? Okay, so let's use this formula. Angular velocity final equals angular velocity initial plus plus the angular acceleration times time. I think that will work. Got everything that goes here. I want that. So initial is 0. Final is we have that as being right 147. So angular velocity final divided by, because that's 0, divided by time, is going to be equal to the angular acceleration. That's 147 radians per second. That's the very end, radians per second, and divided by the time of 1.5 seconds. All right, 1.5 seconds would tell me how many radians per second I'm picking up every second. All right, so 147 divided by 1.5 is going to be 98 radians per second. All right, 98 radians I'm picking up every second per second. All right, that's a 9 right there. Interesting question. Let's do another one. Now, I like this problem because it's a really common industrial type problem. You got motors, got pulleys, things turning around at certain rates. Okay, so it's very common for electric motor hooked up to a different wheel using a belt. This is done typically to change the speed of rotation. If a small wheel is traveling 1870 rounds per minute for 1 minute, answer the question. So this wheel here has 1870 rotations per minute. 1870 rotations per minute. And again, it could be used to change the speed of this wheel. It could also be used to change the workload of the wheel, right? So depends on how the size of these wheels can change the energy distribution. So make things easier to turn. The faster you're turning, then the less more energy is into the spinning, less is into the actual turning of it. But either way, so that's for another conversation. So, all right. So what's the angular velocity of the small wheel? All right. So it's traveling at 1870 rounds per minute. So that's 1 minute. So let's do that. 18. Let's do up here. 1870 revolutions per minute. And let's flip that to get rid of the revs and go to radians. Get rid of the minutes and go to the seconds. And sorry if that's on the edge there, but 2 pi radians is 1 revolution. 1 minute is 60 seconds. So we'll put that right down here. And that's going to give us my revolutions in angles per second. So 1870 times 2 times pi divided by 60 is 195 radians per second. So 195 radians per second. All right. What is the tangential velocity of the small wheel. Okay, that's how fast that small. All students, please report to the comments at this time. All students, please report to the comments at this time. All right, so that's the angular velocity of a small wheel. What's the tangential velocity of that wheel? Okay, well, we've had some of these formulas ready. Velocity tangential is distance divided by time. My distance is the angle traveled times r over time, and that is equal to the angular velocity times r. So I'm going to use this formula, and 195 times r of 0.2 equals, all right, so well, it's 5 centimeters, so I grabbed the wrong one here, but that's 5 divided by 100 would be 0.05 meters. All right, so that thing's spinning around at a pretty quick rate here. 195 times 0.05, 9.7 meters per second. All right. Now, this angular, one thing you want to note about this here is that the distance traveled around this circle, because it's hooked to a belt, is the same as it is on this one. Okay, so this guy here is traveling around pretty quick, but doesn't have a lot of distance around the outside. That distance is being translated to this guy, so this guy has the same amount of distance, but of the larger radius, much less rotations. So how many revolutions per second is a small wheel undergoing? Um, so here we got here. So we just did what's the angular velocity of the small wheel? What's the tangential velocity of the small wheel? We did that. How many revolutions per second has the small wheel undergone? Okay, so how many actual revolutions is giving it for 1 minute? Okay, let's try that. Okay, so actual angular um, displacement is equal to the original angle, which is just 0. So you can drop that off if you'd like. Plus angular velocity times time, and there's no acceleration here. It's just hold out. So angular velocity is going to be 195 times your 60 seconds, and that is going to give me my total amount of angle that I've gone through. 195 times 60 is 11,700 radians. All right, so 11,700 radians, and it wants to know revolutions. So let's convert that guy over to revolutions. 11,700 radians, and get rid of the radians and go to revolutions. Now, this is kind of a backwards problem because we know it's 1870 revolutions per minute, and it's gone for 1 minute. So this is kind of a problem that is, we'll see it here in a moment here. So this is 2 pi radians per 1 revolution. So 11,000 divided by 2 divided by pi, and we're back to the 18. There's a little bit of rounding issues there, but it's pretty close to 1870. Okay, so that's money, yeah, it's 1870. Okay, so we're 1870-ish. Tangential velocity is 9.7. Okay, so maybe we could put a little better question here, but that's showing, do you understand how everything's going around, right? So this is 195. 195. What's the angular velocity of a large wheel? Okay, so let's try that out. Here, I'm going to put this right here now. For this one, the angular velocity, it has the same tangential velocity. That's kind of important. Is equal to the angular velocity times the size of the wheel. I'm using this formula right here. So divide out the tangential velocity divided by r is going to give me the angular velocity. So tangential velocity is going to be the 9.7 meters per second because it's hooked to the same rope, same pulley, divided by 0.2, and this is going to give me this guy. 9.7 times divided by 0.2 is 48 radians per second. All Alright, so 48 radians per second. Radians per second. And let's take a moment here and change this up a little bit. I'm going to maybe remove that question. Say, how many revolutions did the big wheel go through? So it's going 48 radians per second. Okay, so you take the total angle equal to the original angle plus angular velocity times time plus there is no acceleration in 1/2 angular acceleration times time squared. So in this case, how much total angle have I gone through? Let's do that. That's going to be just angular velocity of 48 times 60. And this is going to give me my total amount of angular displacement of that particular big wheel. 48 times 60, 2,910. So this has gone through 2,910 radians. All right, let's go to revolutions. 2,910 radians. Get rid of my radians and go to my revolutions. And this is going to be 2 pi to 1. And finally, all right, we're going to go 2 divided by 2 divided by pi, and we get 463. All right. 463 revolutions. So that's quite a substantial difference than the small wheel of 1870. The last question says you are an engineer. And you are engineering a mechanical device that needs to rotate at 935 RPMs. How big must the wheel be? Okay, so that's a little bit of a challenge question here. Let's just talk about it here for a moment. Okay, essentially we want to rotate backwards. All right, and I'm going to let you figure it out, but I want this number right here to be 935, so you could put that in there. You could then solve for the radians that you need to go through. You could then solve for, we're going to, assuming the time is the same, okay, in 1 minute, saying 935 revolutions per minute. I don't know why the S is on there, RPMs. So you could solve out for the angular velocity, okay. At that point, you can work your way back to eventually the previous one, which would be the size of the wheel. If you have this angular velocity, how big does the wheel need to be? Right there. And that is where you will solve out. You'll have your same tangential velocity. You're still going to have the same 9.7 meters per second. We know we want a specific angular velocity. What does the size of that wheel got to be to make that work? Okay. And that one is for you to kind of give a whirl. Thank you.